And we are back. This is the last day of class. Hard to believe, but we're okay here, getting ready for the final, reviewing for the final, all 15 chapters today. First of all, though, we're grading test 4. Give us a couple days to do that. We'll post the key for it later on. Probably at the end of the week, but look for your score to show up in Learning Suite. Also, quiz 10 is due tonight, the last quiz. That topic, I think, is over chapter 15, the free radical stuff. And then our final is December 17th. I think that's a Thursday, right? It's next week. We have to stay to the schedule, keep it on the same days that are in the university's schedule to make sure that your guys' finals are spread out over that week. 70 questions. There'll be problems that are very similar to the ACS standardized exam. They're very similar to my multiple choice exam. Questions you've already seen. It's normalized to 200 points. It'll take us a little while to grade it, but it'll be a similar thing. You'll have an answer sheet. You'll fill that out and upload that to Learning Suite by midnight on that night, December 17th. But it's over all 15 chapters, right? And that's a good way to prepare. Keep up on your homework book challenge, which is your notebook that has your solutions to all of the even problems at the end of each chapter. You'll certify that on the final. There'll be a checkbox there. Now, we'll only use that if you find yourself in a borderline grade area. Once I plot out all the scores, you guys, your scores create the curve, and I look for natural breaks in those point totals. And if you're in one of those spots, you can then get the next grade up worth 3 to 5 raw points. If I can see your homework book challenge, and we may contact you then and have you send us a couple of the pages electronically to verify that. But normally, not many people in the class will need to have that looked at, but you don't know ahead of time. So it's my way to get you to work more problems, and that's the best way, I think, to help you prepare for the final there. Go back through all the old exams, of course, and brush up on the tougher topics. And that's what we're getting into today. We've got the sample test up here on the overhead, but first let's go to the board and work some problems just in general here. And going back way to the beginning, alkanes. Should keep in mind, of course, the principles of structure, formal charge, Lewis dot, electronegativity, hybridization, pKs, resonance, isomers, all of those issues. But I think looking at, the next level of understanding, reactivity, is really where things come together, right? Because you got to analyze the structure to think about reactivity. And then reactivity is a consequence of the mechanism, what the reagents actually do. So those 3 key areas really fit together. And it's all a consequence of carbon, the amazing thing, right? Carbon, that humble little atom, atom number 6, 4 valence electrons, not too electronegative, not too electropositive, the right size and shape, whatever, to form this vast array of different structures and reactivity that allow life to be possible as well. So very profound consequences. But here we got what, just burning? So a couple of butanes, oxygen, and a spark. What will that form? Yeah, CO2 and water. Now don't forget about that. We didn't balance the equation. We could ask you about that. Here we have a couple of structural isomers, right? N-butane and 2-methylpropane. Which one gives off more heat here? Well, this is going to be the more stable one because of the branching. More like bonding lowers that down. So this will give off less heat. This will give off more heat, actually. So keep that in mind. All right, reactivity. Here we have hydrochlorination of an alkene. And what are we going to get there? We're going to get the more substituted chloride. And that's a consequence of Markovnikov reactivity. The electrophile, which is a proton in this case, goes to the end, and you have the secondary carbocation intermediate, okay? What if we do water and we need sulfuric acid here? Water, sulfuric acid with this, again, will protonate on the end, secondary carbocation, but we have branching here. So what will this end up as? Yeah, this will do a 1-2 shift, a migration to the tertiary carbocation, and then it'll be trapped at that point. So that's a trickier problem. Okay, hydration. If we hydrated this one, we just get isopropyl alcohol, right? But this one, because of the branching, we get that shifting. We can also do the anti-Markovnikov alcohol formation with hydroboration. And in this case, there's no carbocation, and we just go directly to the less substituted alcohol, the primary alcohol in that case. MCPBA, and that's the topic into chapter 12, I think. So these are kind of mixed together, but it's showing you the variety of reactions with alkenes, right? So if we can epoxidize here, and that's a concerted reaction with the carboxylic acid, remember. The byproduct is the carboxylic acid, and it transfers that one oxygen to the alkene to form the epoxide. Okay, and again, you can pause your video here and work on these before I give you the answers here if you'd like to check your understanding. Go back and use this to study from as well. Here we have a chloride with a stereocenter, secondary. So what is that? Is that S? Yeah, I think it's S. Okay, don't forget how to do that. Sodium azide. So here we have N3 anion, the sodium. That kind of gives it away. This is a charged small nucleophile. So this will go, with SN2 reactivity, backside attack, and it will give what? The R product now. T-butoxide is bulky because of the terpyl group, and it's a stronger base, right? The pK of an alcohol is 18 in this case. So the size and the reactivity here is going to what? Give us the elimination product, E2. Okay, that's typical. SN2 is the best one here for primary and secondary, right? E2 occurs with a strong base, okay? And tertiary and secondary are the better ones for that. Methanol, neutral nucleophile now with the same chloride here. What are we going to get? Well, we're going to get a mixture of products. It's going to be DL in this case. Why? Because it's the neutral nucleophile now. It is secondary, so it'll go through a carbocation. What do we call that? SN1. Okay, that's better for tertiary. Okay, but because this is neutral now, and this can form, a stable carbocation secondary. It's slow relative to a tertiary. And the stereocenter, it goes through a flat carbocation. So the methanol can come on top or bottom. Then it loses a proton off there. So there's a little bit more to that mechanism. But yeah, don't forget about, the hallmarks of SN2 versus SN1 versus E2. Notice I don't even have E1 up here. E1 is useless. Non-nucleophilic that just eventually fall apart. And it usually gives a mixture of things. It's not preparatively useful. Probably won't be on the test. But these three will be. Okay, the different things you need to look out there for that. And there'll be a bunch of alkene reactions. If we do the bromination with Br2 of an alkene, we'll get what? We'll get the trans dibromide. And remember, it goes through a bromonium ion and then backside attack. So that's why it gives the trans thing being an anti-type mechanism. Now, if we have chlorine in water, we're going to do the chlorohydrin or the halohydrin reaction. And there we're going to get what? We're going to get the chloride forming again. But as that chloronium ion opens up, you see, we're going to have water attack at the more substituted spot because that's where most of the charge will build up. This is a tertiary position now due to this methyl group being there. But notice it's still anti in this case, okay? Chloronium ion, that's our electrophile. That will form that bridged chloride three-membered ring with a plus charge on chlorine. And that will break open, but as it breaks open, it'll build up charge here, and then across from that, and I'm drawing this behind there. Both of these are DL. The other trans one here and the other trans one here are also present there. Okay, what about osmium tetroxide? So here we're mixing in chapter 12, and with that, similar type of thing. Both sides of the alkene are going to get functionalized, but look at this, osmium tetroxide. Both these oxygens are on osmium, so when it lays down on the alkene, they're both delivered from the same phase. So you get the cis product, and it's also DL, okay, coming in from that same side or from the back side there. It's actually the water step to hydrolyze the osmate ester. So there's more we could say about that mechanism, but the stereochemical outcome and the product outcome is the key thing here. What about HBr? So hydroboration, hydrobromination, hydrohalogenation or whatever, but in the presence of peroxide now, okay? So that's similar to what we just said about hydrochlorination, right? But here we get the less substituted bromide, okay? And that's because it's bromine radical that's being formed after oxygen, the initiation step, the alkoxy radical takes off a hydrogen atom, gives a bromine atom radical. That adds to this fact to give the tertiary radical. So it's a couple steps here we can review, and then you have a tertiary radical here, which propagates the mechanism, grabs another hydrogen atom off there to give the product. I'm not drawing the stereochemistry, but it's cis entrians, and both of them are chiral. So there's a DL pair there. I guess there's, what, 4 possible ones? But don't put the bromide at the tertiary spot. That would be incorrect. All right, let's see. We got a few more already drawn up here. Yeah, it's a lot to review, and we will get to the sample final here in a second. Hydroboration of an alkene like that, what's that going to give? Well, it's going to give the less substituted alcohol. And the first addition here is the hydroboration step, right, which is going to give this syn addition there. And then the oxidation of the intermediate alkyl borane goes with retention of the stereochemistry. So it's indeed the trans product, okay? But it's a less substituted alcohol. Now, if we treat with ozone here, molecular scissors, we'll get the ketone here, methyl ketone, and here we'll get an aldehyde. Why do we get an aldehyde here? Well, there's a hydrogen right here, right? So when we clip that with ozone, 1, 2, 3, 4, 5, count carbons there. That can be kind of tricky. When we ask multiple choice, we can give you a variety of carbonyl products here, especially if there's multiple alkenes. That can be a little tricky. Maybe you saw that on test 4. If those are tough for you, review those. Focus on those harder concepts to help you review here for the final. Okay, here we're doing hydrochlorination of an alkyne. That's a similar thing. Here's our electrophile, which is a proton. Okay, and that proton's going to go on the end, and then chloride's going to attack there. But notice after we do it once, we'll get a vinyl chloride, right? Chloride in the middle, and then we can do it again. There's 2 equivalents here, and we'll get the dihalide at the internal position. That's called a geminal dihalide. They're twins. They're on the same carbon, okay? They don't go out here. We don't get the 1,2 dichloride. We get the 2,2 dichloro product. Now we can hydroborate alkynes also. That's just one hydroboration. And then we'll get a vinyl alcohol, and that vinyl alcohol will actually tautomerize, we say, to the aldehyde. Okay? So there's a couple steps there. The initial intermediate would look like this, right? After we do the hydroboration and then oxidize it here. And then remember, we can transfer that proton, that's called tautomerization, of the vinyl alcohol to the aldehyde. The carbonyl version is more stable than the vinyl alcohol version there. We can also hydrate this alkyne. So it's this substrate here, sorry. Maybe that's getting a little messy there. But if we have this propyne and we hydrate it, again, our electrophile is sulfuric acid. We're going to protonate on the end. Carbocation in the middle, that's where water will go on. And it also tautomerizes, right? But it'll tautomerize this time to the ketone, not the aldehyde. Okay, so it's the keto version there, because we got a different electrophile now. Here the electrophile is actually borane, right? And we're still putting the electrophile on the end. It's the same concept there, but it gives opposite products, just like we know with alcohol hydration and hydroboration. Those are complementary conditions. They give different products. Okay, it's a consequence of the mechanism, though, and how the intermediates are relatively stabilized. Okay, speaking of this, so we got relative kinetics here. I'm telling you, the cis chloroterbutyl cyclohexane is going to be fast with TB toxide. This one's going to be slow. This one's the trans one. Why is that? Well, we've got to look at the chair conformation here. We're going to put the terbutyl in an equatorial position, right? So we're looking down at the top now. This chloride will be up here, what, an axial position. Now notice what, there's two adjacent hydrogens here at the beta position, and that's where TB toxide is going to do its business, right? Going to take the proton off there, and look, that's anti lined up there. So that's going to very quickly go to the alkene product, right? They both go to the same alkene product, but this one's fast because it's lined up anti, or 180 degrees, right, for the dihedral angle. Okay, now don't forget about conformational isomers, these ring flipping things. We talked about the conformations of alkanes, rotating around carbon-carbon single bonds. We have the anti-conformation, the gauche, and the eclipsed. Well, here we've got the similar concept of flipping these back and forth, but the terbutyl has a large A value. It wants to keep it equatorial because it's so bulky. Those A values will be on the data sheet as well. The same data sheet with the NMR shift ranges, some IR frequencies. So don't memorize those things, but know how to apply them and think about those things in the context of problems. So what would this one look like? Well, it would have those guys trans to each other. And notice this one's now equatorial, okay? So it is gauche. It's 60 degrees to both of those. Now, eventually it does eliminate to form the same thing, but it's actually kind of a flattened half chair conformation, okay? And that's higher in energy than this one that's locked in the optimal transition state conformation. So this one's very fast. It can be hundreds of times faster than this one's slow if it's locked in an equatorial position for elimination. Okay, so some analysis there. All right, alcohol reactions. What do we got here? We've got sulfuric acid and heat with an alcohol. We're going to dehydrate that. Remember, that's just loss of water, and that's the consequence with this. Protonating and then losing a proton at the adjacent position and kicking off water at that point, okay? We can also deprotonate alcohols. We're going to talk about acid-base chemistry here. So this will form the alkoxide and hydrogen gas with sodium hydride, and then we can what? React that as an SM2 reaction to give what? The ether, the methyl ether there in that case. So thinking about the mechanism and acid-base chemistry there, we treat an alcohol first with a strong enough base, and that has to have a pKa higher than the pKa of that, which is about 16. So we can't use, acetate or even an amine. Hydroxide's really not very good either. We want to completely and irreversibly form the O minus here. So we use a base that has a conjugate acid with a much higher pKa. This pKa is about 35, right? pKa of the alcohol is about 16. So we always go to the higher number here, the weaker acid, okay? This is a stronger acid than this, which means its conjugate base is strong enough to yank that off. So know some of these pKa numbers. I've given you a couple to memorize. It gives you a benchmark. Carboxylic acids, ammonium cations 9. And from that, structurally, you can usually figure out all the others, or at least estimate what they're going to be. But it, always helps to have a good memory. If you want to memorize some other ones, fine. But I've not given you a sheet to just memorize a bunch of things. I want you to apply the principles. So here we have sodium chromate, bichromate, and sulfuric acid. That's going to form chromic acid in the reaction mixture. This chromic acid can oxidize what? Alcohols to carboxylic acids, okay? And it has to be a primary alcohol in order to do that, to go all the way to the carboxylic acid. Now there's another oxidation state beyond the alcohol that's not all the way to a carboxylic acid, and it's an aldehyde, right? And we can access the aldehydes with PCC, pyridinium chlorochromate. Okay, so yeah, I think that's a good review. Now, there's a issue here, and it's keeping track of all these reagents and all these products. This is a difficult task. I'd like to focus just on one atom here, bromine. How many different reactions have we learned that involve bromine? It's a lot. Let's total them up and go through them and look at the minute details that change the reactivity and the type of reactions we expect from bromine, okay? We've got this one. We've got hydrobromination, right? Adding HBr across here. And that's just it, just the acid, hydrobromic acid, and an alkene. What do we get there? Yeah, we get the Markovnikov product, the more substituted bromine. Okay, that's the first one we covered. And then we did this one involving bromine. But that's Br2, that's molecular bromine. Different outcome here, right? This is the dibromo, the 1,2-dibromo, the vicinal bromide. Different reagent, Br2, HBr. Okay, notice the different outcomes of the products, okay? This is the first couple. How about this one? Br2 and water. And this is the bromohydrin reaction. It'll be the same bromonium ion electrophile intermediate, but water is our nucleophile, not bromide. Or we could use NBS, yet another brominating agent, right? So we don't have to use Br2 here. We can use NBS instead. And what will that give us? Well, bromine will be on the N position. That's the electrophile, remember? And our nucleophile is neutral water in this case. That goes on the internal position. That's our bromohydrin. So we're already up to 3 here. Are there a couple others? Yeah. We've got alkane bromination with heat or light. And the light is a nice thing because you can do it one equivalent and get high selectivity for bromine. And that's different than chlorine. Chlorine's not selective, but here this is selective for the most substituted spot. And in the case of propane, that most substituted spot is the secondary bromide. So what are we up to? 4 already? Well, what about this one? How about NBS? Back to that and light. Now these are the conditions for what? Allylic bromination. So we don't have HBr here. We just have a source of bromine radical, which is what NBS is with light. And initially it takes off a hydrogen atom here. It gives the allylic bromine, and then the allylic radical attacks more NBS. And we get what? We get the allylic bromide. Yet another one. We're up to 5 or so here. We can also take this same alkene with HBr, but in the presence of peroxide. Is that another one? Yeah, we did HBr before. Here it was. But now we're in the presence of peroxide, and we're going to get what? We're going to get the less substituted bromide. Okay. So the bromide parade continues here. What about this one? Alkynes with 2 HBRs. Remember, we can hydrobrominate or hydrochlorinate alkynes with 2 equivalents here, and where do they go? Yeah, the internal spot. Okay. And we can also do 2 equivalents of bromine, molecular bromine, right? And in this case, we'll get 4 bromides on there. Wow, is that it? How many is that? Let's see, 8 reactions just focused on bromine. But if you can keep these straight, look, you can then keep all the ones that are related to chlorine straight, and you can relate these to some other things. The Markovnikov addition with the electrophile going on there, and then the radical ones. But all of these involve forming what? Alkyl bromides, which are very useful synthetically. But notice the little differences, right? Bromine Br2 versus bromine Br2 and water, for example, or bromine Br2 and light with an alkane, okay? So the subtle differences in combinations. So, you know, you might want to do some flashcards or do some extra outlines of the different chapters to keep track of it, my chapter summaries are good starting points for an outline for your chapter, but then keep track of the reactions. And the process of you coming up with those materials will help reinforce these ideas in your mind, and then working these problems in these different chapters. So here I just collected all the bromine reactions and some of those there. Now, one of the tougher concepts here is this bromination of alkenes that depends on the stereochemistry. So this is a tougher one conceptually to look at here. If we have the trans alkene here, where it's symmetric here, the two ends are the same, we get the dibromine. You see the trans arrangement there, bromonium ion, and backside attack opening that up. But look, you've got a center of symmetry here, right? So these stereocenters are opposite each other. And because of the symmetry here, yeah, this is a meso compound. It's achiral. Okay. It's a consequence of that geometry of the alkene. But if you have the cis alkene here, the same thing, look, you're going to get that same anti-mechanism. The two bromides are across from each other, but there's the stereochemistry of the alkene to begin with. But you don't have that internal symmetry anymore. If you rotate around here, you see it a little more clearly, right? You'll see the two stereocenters are actually the same. In this case, I'm drawing the RR, I think. It's also generating the SS. And you see those are chiral. Okay, so this DL pair is there. And that's because of the geometry of this and the consequence of the bromonium ion and the backside opening there. So meso in this case from the trans and chiral there. Now I don't memorize which one goes to meso and which one goes to chiral. I think about it and think about the mechanism and see what it's going to do. And oh yeah, I see the center of symmetry. Or if I rotated around there, I'd see this arrangement where you'd see a mirror plane, right? And again, that's achiral then, okay, because internal symmetry. Here, there's no center of symmetry and there's no mirror plane, okay, because this one's down and this one's up, okay, RR or SS. That's a tougher concept, so focus on that and go through that if you need to. Let's go to the overhead here, Colin, and go through the sample final. So a lot of these are questions that we've used in the past. Most of them are single concept questions. Some are a little tougher. I'll try to point some of those out in your strategy here. Mainly, my main advice, which has been the same over and over again, use your scratch paper, experiment with a problem, draw things out. The process of doing that helps jog loose some information in your mind. There's a real connection between your hand and your mind. So as you engage with the material and draw things out and try different approaches for different problems, your mind will help you out, and you'll be amazed at your power to recall these things. Yeah, there's a lot to keep track of here, and it can be difficult, but if you focus on the core principles, thinking about structure and hybridization, sp3, sp2, sp, what is that? And the shape-wise, what's the geometry and what are the constraints of the mechanism, for example? But it helps to draw those out and engage with it, just like we did here with the cis and the trans 2-butene. So let's go through some of these formal charges. Know how to come up with that. So here I think it's A, 1 and 3. Yeah, so there's a plus charge here and a plus charge here. You know how to apply that formula. Here, you just got to add up the atoms. Not all the hydrogens are shown, right? Double bond and ethylene. Yeah, so sp2 hybridized, sigma and 2 p's for the pi bond. Okay, remember a double bond is a combination of a sigma and a pi bond. Correct name, yeah, and most of the nomenclature will be relatively simple, minimizing branching in this case. So you'd want a number through here. Call that C. You call that an ethyl group, and this methyl here. If you numbered through here, you'd have an isopropyl with more branching. Okay, that's one of the little more detailed rules. Here you got to draw it out, I think. Primary and tertiary carbons. 2,3-dimethylbutane, yeah, if you draw that out. Here are dipole moments. These are fixed, so your dipole moments contribute to the overall dipole moment of the molecule. So you look at the individual bonds. Here they're canceling out. They're pulling across from each other. And here there's 4 all pulling in equal opposite directions. But here, the 2 together on the side of the benzene ring will make that the more polar one. Let's see, properties here. Boiling points, the branched alkane is the lowest one because it's nonpolar. And then the non-branched one, and then what? The branched alcohol. The secondary alcohol can't hydrogen bond as well as the primary one can hydrogen bond very well. So that has what? The highest boiling point. Yeah, so I think it's D. Naming, including stereochemistry, RNS. Yep. pKa. So this is just structure-wise. You know, I don't know if you need to memorize those, but you know this one. I told you to memorize carboxylic acid, which is 5, right? And that's a consequence of resonance and electronegativity. It's always the stability of the conjugate base that's left behind as the proton comes off. All of these have protons. It's not a consequence of the proton. It's a consequence of the conjugate base. So here you have the carboxylate anion, resonance stabilized pK of 5. This pK is 50. If you left behind a negative charge on this nonpolar carbon, that's very, very non-acidic. So it's a very high number, right? Remember, the pKa is minus the log of the Ka. It's an inverse scale. Here you have a couple of electronegative oxygens, right? You might think, well, those are going to be similar. No, the pK of phenol is 10. It's lower than an alcohol, which is 16. Why? Because of resonance. Once you form the anion here, you can delocalize those electrons in there. Chapter 15, monochlorination. There's one here. All 4 methyls are the same. And then the methynes are the same. That's 2. And then the methylene there. So I think it's just 3 structural isomers. Okay, E2, most likely with a tertiary halide. Yep, hindered strong base. And that's the hallmark of t-butoxide, right? So know what the key typical outcomes will be for the 3 key reactions here. Which alkene will react fastest with an electrophile? Well, it's the more electron-rich one. That'll be the tetrasubstitute alkene. That reaction's done in seconds. These will take a little bit longer. Oh, the trisubstitute one would be okay. This one, 13. You really got to draw this out. You got to link these up, and maybe we'll go back to the board. But this is A. If you draw out these structures, you'll see when ozone cleaves both the sigma bond and the pi bond, these fragments will be left behind. So you'll have like this molecule in the middle here of A, this nonadiene, and then you just link these 2 guys up on there, okay? So this one generates, 2 carbonyls there because it's in the middle. The 2 alkenes, 2,6-nonadiene. So if you draw out the structures, you'll see those. So there's where you need to use your scratch paper, one like that. You can't really see right away based on the naming there. This really combines 2 concepts, right? Nomenclature and reactivity with ozone, O3. Okay. Let's see, this one, how many total stereoisomers, including enantiomers and diastereomers, would there be here? Well, there you have to count up the number of stereocenters in a molecule. They're not defined here, but that's a stereocenter. That's one. Don't forget about that one. That's the one that's easily missed, I think. That is a stereocenter right there. Then that one and that one. So that's a total of what, 5? So 2 to the 5th power is 32. Okay, so 2 times 2, 4 times 2 again, what, 8, 16, 32, 64. Goes up geometrically. Which can be a real complication with molecules that are more complex. And then we got the SN2. Here's the hallmark for SN2, fastest for SN2. Well, that's backside attack bimolecular, so you want one that's less hindered, right? So I think A is the primary one without branching. This one's primary, but that's branch point here next door will slow this one down, even though it's primary. This one's secondary. It's a lot harder to hit the back of that. And this one here, it's impossible. Hit the back there. This one will ionize first. Okay. This one's a little tricky. It's a double SN2 reaction. So we have sodium sulfide, which has a double negative charge on sulfur. And you see the 4 products, they're all sulfides, right? So we have to do one displacement and then another displacement. So if you look at this and analyze it, this is the SS dibromide, and the product here, C, is the RR product. So if you cite R and S to these and go through the rules here, you'll see that. The first one you can kind of see if you do the backside attack there, you see right now, and you know, it's drawn kind of different there, but this is S, yep, and here it's R. You got to rotate from down below there, and you can see that as RR. NMR question, how many different sets here of protons in this compound? 1, 2, 3, 4, 5. These two methyls are different because one is cis to the carbonyl, one is trans. So those will have different shifts. Those are different sets. You've got to apply symmetry there. So what did we say? I think it's 5. Yeah, B. This one here, SN1. What's the consequence there? Well, it has to ionize first. So the neutral nucleophile, ethanol, okay? So which one's going to ionize better, a vinyl cation, an allylic cation, secondary cation, or primary cation? Right, the allylic secondary. Okay, so B there. Which one's the more stable cation for SN1? Okay, yeah, this one's okay. You tosylate that, turn that into a leaving group, and then what, SN2? Yep, and that would be C right there. Here's one that's a little tricky. We got the epoxide, and how do we open this up? Look, with the azide, it's going to be our nucleophile, and look, it's at the more substituted spot, and the alcohol ends up at the less substituted spot, so we're opening it up here. So what does this look like? Well, if we used azide as a strong nucleophile, as a charged N3 anion, it would open up here at the secondary spot. But that's not where we're showing it here. But we're asking about this product. How do we do that? Condition, right, we use hydroazidic acid. So this will first protonate the epoxide, and then as it opens up, you'll have azide going in from the backside, because this is where more positive charge will build up in the carbocation, okay? And it gives the trans product normally. Actually, it gives a mixture, cis and trans. The trans one's normally more favored, but that's where the positive charge will build up from the protonated epoxide. Okay, so B is the correct answer there. Then we got conformational questions. The lowest energy one, you want to make sure you're not eclipsing anything like C and D. These are eclipsed conformation. You want to be in staggered for the lowest. Okay, then you want to make sure you're talking about the right compound here. And this is, yeah, 2-methylbutane right there, looking down that conformation. You only have one gauche interaction here, okay, which is a little bit higher in energy, but all of the conformations rotating around there will always have a gauche, at least one. If you rotate all the way around here, you can have conformations with 2 gauche interactions. So there, using your models, your scratch paper can be helpful, I think. We already did one like this. Right, it's going to be their Markovnikov product C. And how about this one here? This is what, bromohydrin formation. So bromonium ion bridging here, and then bromonium ion water can come on the top at the tertiary position, and that will give these two across from each other, anti to each other. So I think B is your correct answer there. Yep. And the nucleophile goes to the more substitute spot. Then we got this one, which is that rearrangement thing. We got protonation and then a hydride shift to give the tertiary carbocation. That's where the alcohol forms D right there. Hydroboration, already did one similar to the 25 there. Oh, which base cannot deprotonate acetylene? Acetylene's what? The terminal alkyne, the pK is 25. So you need one that forms a conjugate acid here, which is higher than 25, okay? And certainly that one can. That's a very strong base being organolithium. Sodium amide, yeah, that pK of ammonia is 38. Sodium hydroxide, no, because water pK is 15. Okay, that's lower than 25 for acetylene. Yeah, methyl lithium certainly can do it there, and that's pK of methane, which is 50. So that can do it. So the question is, which one cannot deprotonate acetylene? I'd say it's C. Yeah. Here we have hydroboration of the alkyne and then tautomerization, I think, to A there, yeah. Strongest acid, well, they're all carboxylic acids, but it's how stable the resulting conjugate base is, right? And if you have more electronegative groups closer to that anion inductively through space, these will help stabilize that and lower that pKa. pKa of this one, I think, is around 2. These others, this one's comparable to just regular acetic acid, around 5. This one's maybe 4 or so. And this one, they're too far apart, too far away. Proximity helps the inductive stabilization. This one's similar. We've got acid conditions here with the neutral nucleophile. So we're going to protonate the epoxide and then backside attack at the tertiary position with what? With methanol. So that's where our ether is going to be, the methyl ether, and these are going to be across from each other. So is that C? Yeah, C is the correct one there. The answers are at the back of the exam if you've looked at it. So I'm not showing you the answers here. The key is at the back of the exam here. Single compound upon treatment with chlorine under photolytic conditions, at room temperature. So these are just one set. So yeah, just form the chlorocyclopentane here. Here you got 3 different compounds that can result. Here you got 2 that would result. Here you got 1, 2, 4, 5 different isomeric chlorides that could form. This one's a little tricky, I think. Alkane bromination compared to chlorination, highly selective process. What's the main factor here? The slow step in bromination, exothermic. The slow step in bromination is endothermic. Yeah, and that's that propagation step. Both of those are, the first one's endothermic for bromine, but it's exothermic for chlorine, which makes it less selective by the Hammond postulate. So I think it's B there, okay? Which will react faster with methanol? So that's neutral methanol. So what type of reaction are we talking about? Yeah, SN1. So which one would give a more stable carbocation intermediate upon loss of bromide? It would be D, tertiary bromide. Select the product here. Well, this is a tertiary bromide, again, with a charged but small base, okay? But look, this is tertiary here, so this backside attack is going to be hard. And what's going to occur, because this is highly basic, pK of methanol is what, around 15, 16. The optimal range for charged nucleophiles, and being small is a key factor there too, is 5 to 15. 15, we're on the highly basic end of that. So B, especially being tertiary bromide, it's going to eliminate and form the alkene product. Okay. Splitting NMR, so there's a lot of different ways we can ask NMR. Yeah, we can either show spectra or ask about different things here. Splitting pattern for these indicated hydrogens right here. How many neighbors do they have? Well, they just have the 1. So I think N+1 rule, it'll be a doublet, B there. Infrared light that's absorbed here, that's bond lengths and angles being set in motion there. So we have the bond angle bending and the bond angle stretching, that we call there. And that's, yeah, the IR, so that's C, right? This one here is a little bit tricky. It says upon hydrogenation, it gives a new product here. Alkanes, this product is also optically active. So if you hydrogenate this one or this one, those give achiral things. In fact, they start out achiral. So A and B can be ruled out. So upon hydrogenation here, you'll have an ethyl and an ethyl. This doesn't become a stereocenter then if it hydrogenates. This one, though, if you hydrogenate, it still stays the same what? S in antimer. So this is the one that fits the bill here for the description. Now that's a little tricky. You know, read through it and maybe use your scratch paper to hydrogenate all 4 of these and then see which one is still optically active or chiral, right? Select the chiral molecule here. You got mirror plane symmetry there, and you got a mirror plane there. This one's highly symmetric here. Then you got a mirror plane there. But no mirror planes here, so D is the chiral one, right? 1600, so yeah, you'll have an IR numbers on the data sheet, and this one corresponds to a carbon-carbon double bond stretch. Remember the carbonyl is carbon-oxygen. Double bond stretches are around, what, 1700? Triple bond here for a nitrile or an alkyne is what, around 2200? So you probably worked enough problems to know that. And the big hallmark here for an alcohol is what, 3500, and very broad because of hydrogen bonding and the change of the dipole moment. Here you can kind of figure this out. So it's a line list here for the NMR data. You got a doublet, 1.7, 3 hydrogens, multiplet at 4, and a doublet way up at 5.5. So yeah, this one just shift-wise, you can already tell you up here around 6. It better have two electronegative groups next to it, yeah. And then just what, one neighbor? Yeah, it's a doublet. So you can already figure out, I think it's D, yeah, just based on that downfield shift. And then this methyl group here has one neighbor, so it's a doublet also. Where is it? Yeah, doublet right there. So the line list data can help you out. MCPBA, we're forming an epoxide again, a lot of epoxide reaction. And now we're using a charged nucleophile, so it's going to attack at the less substitute spot. So there's where our cyanide's going to be, right? And the cyanide and the alcohol are going to be across from each other or trans to each other, consequence of the mechanism. So I think it's B, yeah, B. Okay, chloronium ion, correct Lewis dot structure, that would be, what, this one here? Yeah, where the other lone pair bridges over. And there you just apply the formal charge. You can remember your formal charge thing there. This one has too many electrons on it. This one has the plus charge on carbon. No, it's not there or there. Okay. This one is incorrectly keyed at the end. This is, sorry about that. A is the correct answer here because it's a Z alkene. And that stereocenter is S at this position here. So you can go through that. It's a harder nomenclature problem. Normally, you don't even need to list what the alkene is in a small ring. It's always cis, but yeah. Yeah, we got to move a little quicker here. Sorry there. How many stereocenters again? The enantiomer is all inverted. Oh, here's we got chair cyclohexane. They're trans to each other. So the down position, I'd say that one's down, and yeah, that one's up. Make sure they're still 1,3 to each other. Yep. And these are trans. Yep. So I think it's C. Electrophilic alkene additions, the pi electrons function as a nucleophile. The halide is the electrophile. DL pair here, I think it's both of these trans here, both chiral. So those are the two enantiomers A and C. So D is the correct answer. Here with the ozonolysis, you know, which one, alkene-wise, gives this product? So you just connect up the carbonyl carbons and put an alkene double bond there, and that will be, what, a 5-membered ring with one with a methyl? That's one we did on the board. I think it's C, yeah. And the mechanism, knowing enough about the mechanism, what is this? SN2 reaction, hydroxide charged nucleophile, secondary is okay. And so that's going to bring it on, and yeah, lone pair, yeah, double-headed arrows, and then the electrons going up on bromine, so A, yeah. E2 definitions, yeah, we already mentioned that. Select the product, this is the Linlar half reduction, so both hydrogens on the same side, so cis alkene there, yeah. Let's see, radical. So here we have anti-Markovnikov hydrobromination under peroxide conditions. So we're going to form the radical at this point after bromine radical adds to the end. So that would be our key intermediate D, okay? Not these others. It's not heterolytic chemistry, it's homolytic chemistry, but this one here doesn't make any sense, okay? This is not coming from an alkene. This would come from an alkyne, actually. We didn't cover that reaction. And here we got polymer formation. Here we're showing the polymer and asking what monomer gave rise to this. Was it styrene? Was it methyl propene? Was it ethylene or propene? And you see it's 1,3. The methyls are 1,3 to each other. And it's just methyls on the alternating carbons, so it came from propene. Okay, so this is polypropylene in that case. Okay, select the results of the sequence of reactions. So here we have hydration. So strong acid and water, we're going to form the secondary alcohol. We're going to tosylate that alcohol, form a leaving group at that secondary spot. Then sodium acetate is our nucleophile, SN2, and it will be C, our product. Okay. So here we have branching, and yeah, we talked about one like that. In general, alkene treated with H-peroxide, the less substituted alcohols formed. Yeah. Yeah, and here we have an NMR question. I think B is the correct one. You see a couple doublets here. This one's bigger. We're not giving you the integration here, so you just have to, based on the multiplicity pattern, figure out which is which. But you can see this is bigger here, then this doublet smaller. Sometimes you can use that to help you out, but yeah, if we gave you 6H, 3H, 1H, 1H, that would have been helpful here. But a lot of times with these simpler compounds, you can figure out these NMR questions just from the multiplicity, which is an advantage there. This one, why is this IR signal relatively low here? Carbonyls, and all of these have carbonyls. Normally there's 1700. But this one's resonance conjugated to this. Okay, so you can resonate these pi electrons over here and even from the benzene ring. And that will lower the bond order here and make it a lower frequency for this carbon-oxygen carbonyl stretch. So there are factors about the structure that can change the frequencies a little bit. Okay. Here, opening up the POC side, we want to add a strong hydride nucleophile, and that would be LAH. Here, what are we doing? We're doing the bromination at the tertiary position, and we're forming an alkene right here on the side, the Zaitsev, the more substituted alkene. Then we're doing osmium tetroxide water, so we're going to form the cis diol right here, A63, right? Yeah. And then the sequence of reactions here. So these are multi-step synthesis problems, right? So here, if we put an ethyl group on here, alkylation reaction, then do the Lindlar hydrogenation, we'll have a cis double bond there. And then what's this? This is per acetic acid. So that's the same as MCPBA. That will do epoxidation reaction. So draw that out. The CO3, that's a carbonyl and then a peroxygen bond. Remember, those guys do epoxidations. It'll be this one here, okay? It'll be DL, but it'll have the methyl and the ethyl cis to each other, okay? Because of the cis alkene that forms upon the Lindlar thing. And then the radical chlorination here, I think, is not a step, is A there. We don't just pull that off as a hydrogen radical and a propyl radical. Here's the first propagation step. Here's the second propagation step, and this is the initiation step for that mechanism. SN1 involves what? Formation of carbocation in the slow step. That sounds right, but read all the others. Attack by the nucleophile at the less hindered position? No, it's at the more hindered. Backside attack on the sigma bond? No, that's SN2. Filling the HOMO and LUMO of Sonny Bono? No, sorry. He was a 60s rock star. Sorry about that one. Tried to be funny there, but failed, obviously. Alkyne treated with HBr terminal-wise with excess. Yeah, you're going to get the 2,2-dibromo forming there, right? We talked about that. Newman projection. Now, these are kind of tricky. So in the front here, you got the N carbon, and then the 2 position in, you've got 2 more methyl. So that's a tert-butyl. You can already see tert-butyls here and here. And then you've got the other one there, and then an ethyl on the end. And the other one has a group on it. So if you make a model, you'll get to this, and you're looking down this bond right here. You can see the ethyl right there, and the methyl right there. And this carbon right here is in the back of that circle. So yeah, some of those, it's best to make models or make sure you identify which bond you're looking down. IUPAC name here, I think C is correct. Most heat of combustion. The most heat, so this is the one that's the least stable, least substituted, so that would be what, D. And then we gave you a bonus question. How many signals here? And the C13 NMR for methyl cyclohexane. If you draw out the structure, the methyl's 1, the methine is 1, then you have 2 methylene sets, and then another methylene at the 4 position away from the methyl, and that comes out to 5 distinct signal. So you got some symmetry there. But again, scratch paper, draw that out, you should be fine. And again, on this key here, what was the one that was miskeyed? It was 42 that is listed as B. That's incorrect. That should be A. So, yeah. But this is a good exam. It's comprehensive. It covers all the topics. It's got some harder problems. It's got, single concept, simpler, more direct problems. But, you need to look through that and prepare in a comprehensive way, going through all 15 chapters, and that should help you out there. So hopefully, this has been helpful for you. I've grouped the reactions and worked enough problems, I think, in different ways to help you identify where your weaknesses might be. And that's always my advice as well. Use your scratch paper and study-wise, focus on the harder problems. A lot of times students just want to work the problems they like, the ones they've already mastered, and that's fine. You need to review those as well. But delve into the tougher problems. Those are the ones that are really going to help you prepare for the test better. Don't just sit there and hope that those harder problems go away. Okay, they won't. There'll be a couple of those harder problems to work there. So very good. We'll end it there. I'm still doing office hours, so you can still Zoom in on Thursday, tomorrow, or next Tuesday. I'll be having office hours. But we don't have the regular recitation sessions anymore, but we do have the help sessions. Okay, so the TA help room is still active. You can zoom in to that. So we still have ways to help you out there. Or email me if you got specific questions and we can help you out. So very good. You've been a great class. Thank you, and good luck on the final.